Hello, this is our final project, the Wind Energy Project. Our group members are Victoria Basham, Austin Jones, Alan Taylor, and Matthew Goodson. For the outline, we're going to start with our motivation and then move on to our project objective. After that, we're going to give a little bit of background on our project. We're then going to move on to the methodology that we made, and then we're going to show the results and discussion from that methodology, and then we'll conclude. For the motivation, pollution and global warming are getting worse by the day, so the only way forward is with greener solutions. This is why we researched and calculated the wind turbine size required for the Tyler area to supply the amount of power needed. Any engineer wishing to employ renewable energy systems must first perform a cost analysis to be sure of the sustainability and long-term potential of the project. For the project objective, the objective of this project is to size a wind turbine and to find the overall efficiency and energy produced based on weather data from the selected area, Tyler, Texas, to charge a hydrogen tank in a car for 10 total cars. On top of this, a thorough cost analysis on the development and implementation of our wind energy system was performed. This will ensure that the project is profitable and economically feasible.
This project encompasses a comprehensive analysis of the technical aspects of utilizing wind turbine technology to charge hydrogen tanks in multiple vehicles. Below is the steps that were done to accomplish this. First, we determined the amount of power it takes to produce 1 kilogram of hydrogen. Second, that value was used on the electrolyzer to find the required power to run said electrolyzer. Third, our local wind speed data was found. And fourth, using assumed efficiency values, the diameter and area of the turbine using the wind speed data and the calculated power was found. 5, we designed the batteries, inverter, water tank, and hydrogen tank based off the 10 total Toyota Mirais. And number 6, based off all calculations and selected products, an economic analysis was performed to find the payback period, EUAC, and profitability of this project. Background, wind energy technology is a pivotal player in global shift toward renewable energy sources, harnessing the power of wind to generate electricity. Its operational principle involves converting the kinetic energy of moving air into electrical power through the use of wind turbines. Similar to solar, it has witnessed substantial growth due to technological advancements, cost reduction, and an increased emphasis on environmental considerations. Wind energy contributes significantly to environmental stability, and by harnessing wind power, it helps mitigate carbon emissions, aligning the global efforts to create a more sustainable and eco-friendly energy infrastructure. Here we have our laid out voltages, amps, and watts for our turbine, electrolyzer, batteries, and inverter, along with some data on our water tank and hydrogen tank. Through the design, we have sized the turbine, size the electrolyzer, the battery, the inverter, the tank, and the water and hydrogen tank. Below are some key equations we use for the project. The first in the top left is going to be for calculating the power and area of the wind turbine. And the two below them are going to be for the economic analysis with our payback period in EUAC. And some assumptions we've made is that the generator is 80% efficient, bearings are 95% efficient, electrolyzer is 70% efficient. We have a standard air density of 1.225 kilograms per meter squared. Our inflation rate is 2.68%, and our maintenance cost is $2,000 a year.
So with the cost analysis section, we were tasked to find a couple different things. One is the EUAC, another is the levelized energy cost, the LEC, and the payback period. The payback period is you kind of two ways to look at it. You can have the initial investment plus minus the annual negatives of maintaining the system divided by the annual revenue of the system, or you can just look at it as initial investment divided by the net cash movement, so your pluses and your minuses. And the levelized energy cost is basically how much it's going to cost per year, or how much it's going to cost per kilowatt hour after all of your net cash flow is taken into consideration. So just with like water, just the cost of producing the fuel, no maintenance costs, no nothing, like a pure cost of it was around like roughly a cent per kilowatt hour. But the levelized energy cost, it takes into account a lot of other things, maintenance costs, just possible unforeseen stuff, and it came out to around 6 cents per kilowatt hour. So levelized energy cost kind of takes everything into account. The EUAC is your sort of like your total annual minuses for the year. And we also did a separate analysis because since this is hydrogen, you can sell it at a higher rate per kilowatt hour, like because people would have to make the investment of an electrolyzer. So if you were to sell it to people, you wouldn't sell it at a normal just kilowatt hour like rate. You know, like you can kind of charge more, and the payback period significantly decreased. It went from around roughly 9 years to 4 years if you just kind of chose, you know, just a non-usurious amount for the kilowatt hours. Here's our chart for how we size the rest of the system. Is your inverters and your batteries, and we were able to calculate the amount of time it would take to fill the hydrogen tanks, around 7 days. And yeah, here's some more data. So kind of reiterating, we already went over. Here's the total cost of water per year, and the comparison between the grid rate and the wind turbine rate, cost of production. The wind turbine rate right here is just factoring in how much water it would cost per year. This is how this is done.
For our results and discussion, the team discovered with our cost analysis that we had an annual water cost of $2,700, an annual maintenance cost of $2,000, and an annual revenue with respect to grid power of $19,957. The component and labor costs came out to be $118,181. This establishes a payback period of 8.94 years and an EUAC of minus 9,472. The team determined that if electricity was sold at about 30 cents per kilowatt hour, the payback period could be considerably shortened to 3.88 years. This is our flowchart for our hydrogen production. First you have the wind, which powers the turbine, generates electricity into the batteries, which goes through the inverter and the electrolyzers, which uses the water tank to create hydrogen to power these 10 Toyota Mirais. For our results and discussion, with a 70% efficient electrolyzer, it was found that we would need 52.94 kilowatt hours per kilogram of hydrogen produced. To produce the required 56 kilograms of hydrogen in a reasonable amount of time, it was determined 2 of the selected electrolyzers were needed. With the power draw of the electrolyzers, it was decided that the output of the wind turbine needed to be 17.7 kilowatts, and the diameter of the blades must be 31.02 meters. With the selected batteries, 90 are required to store enough power to produce the required amount of hydrogen. To produce 56 kilograms of hydrogen, 504 liters of water must be available of the 6.97 day period. In conclusion, the team determined that it would be feasible to supply enough hydrogen from electrolyzers to these 10 cars using the power generated from a roughly 31.02 meter diameter wind turbine, given enough time, which would be around 6.97 days. The cost analysis of the design system saw profits being incurred at 3.88 years, making this a worthwhile and profitable endeavor. And these are our references. Thank you.